Hi, I'm Dr. Jonaki Ghosh, faculty at the Department of Elementary Education, Lady Shri College for Women, where I teach courses on mathematics education. In this video session, I'll be talking to you about algebraic thinking, which is a very important topic in the Pedagogy of Mathematics course. Now, through this presentation, I'll be using PowerPoint slides, and I request you to bear with me while I set this up. Right. So as I mentioned, the topic is algebraic thinking, and this will be divided into two parts. In the first part, we'll be discussing about what is algebraic thinking, specifically what is a pattern, what does abstracting and generalizing patterns entail. We'll further deliberate upon how generalizing is the core of algebraic thinking. Then we'll go on to generalization by analogy and extension. And finally, how can children's thinking be scaffolded towards generalization? So what is algebraic thinking? Algebra has been described as the gatekeeper to higher education in mathematics. And in fact, it forms a foundation for almost all topics in higher mathematics. Even in school mathematics, topics such as coordinate geometry, trigonometry, and calculus require the knowledge of algebra. So without algebra, one cannot even access secondary school mathematics. Typically, there are two approaches to defining algebraic thinking. Algebra as generalized arithmetic, which is identifying and extending a pattern, followed by finding a rule. And then there's the functional approach, where algebra is treated as a study of functional relationship between quantities. So what do we mean by a pattern? Let us understand the word itself. I'll be giving you a few statements. Which of the following statements, in your opinion, best represents the meaning of the word pattern? A series of actions or events that together show how things normally happen or are done. A decorative design which shows some kind of repetition. Or things or objects that are arranged according to a certain rule. For example, a sequence of numbers or a collection of shapes. Which one of these do you think best describes the meaning of the word pattern? Well, if you reflect for a few moments, you might think that all of these in some way represent pattern. A pattern could, for example, be a set of lines, shapes, or colors that are repeated in regular intervals. Now, in children's worksheets, very often we find these linear patterns where there are colored shapes and the child has to color the last shape in this linear pattern. And or it could be a two-dimensional layout of tiles as shown here. Both of these are patterns, and there could be numerous other things which can be described as examples of patterns. A pattern could also be a sequence of alphabets or numbers. For example, the sequence of alphabets B, C, D, A, A, B, C, D, A, A, and so on, or the sequence of numbers 3, 7, 11, 15. What kind of questions can we ask if we show such sequences to children? We could ask, for example, what is the rule or pattern in these above sequences? Can the rule be used to predict the next few numbers of the sequence? Can we predict the 50th letter of the sequence of alphabets or the 65th number of the sequence? These are some of the typical questions that we could ask children if we give them such kinds of sequences. But why is understanding patterns important for learning mathematics? Well, understanding patterns leads to understanding structure and relationships. Repeating patterns help to develop ideas of sequencing and regularity, as we will see further. Now, if we look at, again, going back to this sequence of alphabets B, C, D, A, A, and so on, we find that the unit B, C, D, A, A repeats itself. Again, if we look at the number sequence 3, 7, 11, 15, we find that every number in this sequence is 4 more than the previous one. So the thinking involved in extending a pattern is a prerequisite to algebraic thinking. Now, let us look at this interesting sequence of shapes and let's treat it as a pattern. And let's answer the following questions. So as you can see, there are green squares followed by triangles, and this is repeated throughout. And let us imagine this to be repeated indefinitely. Now, what are the interesting, insightful questions we can ask students based on this linear pattern of shapes? So for example, one question could be, which is the 15th shape or the 17th or the 33rd shape in this sequence? Now, normally the tendency would be to ask, what are the next few shapes in this sequence? But if we really want students to generalize this pattern, we could ask these questions. Or in what position will the 12th square appear? In what position will the 18th triangle appear? Or how many squares and triangles will there be in the first 120 terms of the sequence? Now let us look at this sequence again. You would observe that in this sequence, what is repeating itself are 3 green squares and 2 orange triangles. And typically, this unit of 5 shapes is what is constantly repeating itself. And you would also notice, if you really generalize this pattern, that every 5th shape is a triangle. So if somebody were to ask, what is the 15th shape in the sequence, you would directly say it is a triangle. But if somebody were to ask you, what is the 17th shape, then you know that the 15th shape is a triangle, and 2 shapes after that, we would get a square, a green square, and so on. The answer to this, in what position will the 12th square appear? Now again, here we have to use the fact that this unit of 5 shapes repeats itself. In every unit of 5 shapes, we have 3 green squares followed by 2 orange triangles. Now every unit has 3 green squares, so to get 12 squares in all, we would need this unit to repeat itself 4 times. And then we can compute that the 12th square will actually be the 18th shape of the sequence. So these questions are far more insightful than asking what are the immediately next few shapes coming up in the sequence. Let's look at this last question. How many squares and triangles will there be in the first 120 terms of this sequence? Now, again, we will have to use the fact that this shape, this unit of 5 shapes repeats itself. So 120 terms means that this unit will repeat itself 24 times. And in 24 such units, we will be having 24 into 3 squares and 24 into 2 triangles. So even with a simple sequence of shapes, we can ask some interesting questions which will really encourage algebraic thinking in children. So what is really required to generalize a pattern? In this case, to generalize the sequence of shapes, we need to be able to make the following observations. Firstly, squares are green and triangles are orange throughout the sequence. Squares appear in groups of 3 and triangles appear in pairs. The unit of repeat is this set of 5 shapes, that is the 3 green squares followed by the 2 orange triangles, which constantly keeps repeating itself. And identifying this unit is fundamental to extending and generalizing the sequence. So in general, what does generalizing a pattern entail? Generalizing a pattern is actually a process of abstraction. And what is that? We need to identify a commonality on some elements of a sequence. So in this case, the commonality was that squares are green throughout and they occur in groups of 3, and the triangles occur in pairs and they are orange in color. To understand that this commonality applies to all the terms of this sequence. Then, to recognize the unit of repeat and to use it to predict the next few terms of a sequence. That is exactly what we did with the sequence of shapes. And then to be able to find or predict any term of the sequence. So we really extended it to the 33rd term of the sequence, or we even predicted that in 120 terms of this sequence of shapes, how many squares will there be and how many triangles will there be, and so on. Now, generalization is actually of 2 kinds. one is referred to as a generalization by analogy. It requires recursive thinking. For example, to be able to identify the next few terms of a sequence of numbers, let us say 2, 5, 8, 11, and so on, is actually generalization by analogy, where you're asking the person to predict the next few terms in the sequence. Or given this nice growing pattern of diamonds or rhombuses, if you like, which comprises of dashes, we could ask the question, draw the next 2 shapes in this growing sequence, or predict the number of dashes in the next 4 shapes. As you can see that each one of these rhombuses are made of small dashes, which are on the boundary and as well as on the diagonals inside. So you could ask children to predict how many such dashes will be there in the next 2 or 3 shapes. But whatever you do, you're asking about the next few terms of the sequence, and that is generalization by analogy. The second kind of generalization is referred to as generalization by extension. And what does this entail? It requires explicit thinking. Now, for the same sequence 2, 5, 8, 11, if we ask somebody to predict the 50th term or the 63rd term, or in general, write the nth term of the sequence, then that will be referred to as generalization by extension. Again, coming back to this sequence of rhombuses, this growing sequence, if we ask how many dashes will be there in the 100th shape, so you're actually asking about the general term of this sequence, or find a rule for the number of dashes in any diamond or any rhombus. That is generalization by extension. Now let us see how children's thinking can be scaffolded. I'll just narrate a small episode of a task which was done with grade 6 children. So 30 students of class 6 were given the task of extending a growing sequence of matchstick patterns, which are taken from the NCERT textbook. So as you can see, there are 3 stages of this growing matchstick pattern. The task required the students to predict the number of matchsticks needed in the next few stages of the sequence. So it's like generalization by analogy. And they were asked questions like, how many matchsticks will be required for the 5th, 8th, or 10th stages of this pattern? Or how many triangles will be there in the 10th stage? So as you can see that the matchsticks enclose triangular regions. So in the first stage, there is 1 triangle. In the second stage, there are 2 triangles, but there are 5 matchsticks. In the third stage, there are 3 triangles and 7 matchsticks, and so on. You could also ask, let us say if there are 19 matchsticks, how many triangles can we have and what stage of the pattern will it be? So these were the typical questions which were asked in the textbook. And let us see how the children attempted this. The strategies used by them were as follows. Some students attempted the task pictorially by drawing the next 2 or 3 stages. So they kept adding matchsticks to the previous stage to get the new stage. And they made the observation that 2 matchsticks have to be added to a particular stage to obtain the next stage. Others counted the number of matchsticks in the first 3 stages and obtained the sequence of numbers 3, 5, 7, and so on, which has a constant difference of 2. And they concluded, using this constant difference, that the number of matchsticks required for the next 3 stages would be 9, 11, and 13, respectively. Now, in both these approaches, the students observed the +2 pattern, because at every stage, 2 matchsticks are getting added. So they observed the +2 pattern and focused on predicting the next few stages using this pattern. And throughout, they were engaging in generalization by analogy. Now, when they were asked to predict a term which was further away, let us say the 18th term or the 30th term, they realized that this +2 pattern would be a bit cumbersome. Although some of them agreed that you could just keep on adding 2, but some said that what if you were asked to find the 90th term and so on. So +2 would become very cumbersome to do. So to transition the students towards finding a general rule or a general term, which is referred to as generalization by extension, students were asked to relate the number of triangles at each stage with the number of matchsticks. And here, a tabular representation of the pictorial pattern really helped. So they were asked to fill in a table like this, where in the first row, they had to fill in the number of triangles at each stage. And in the second row, they had to fill in the number of matchsticks. So as you could see, in the first stage, there was 1 triangle and 3 matchsticks. In the second stage, there were 2 triangles and 5 matchsticks, and so on. Then they were asked to relate the corresponding numbers in the table. That is, they had to relate 1 with 3, 2 with 5, 3 with 7. So it was more like relational thinking, trying to relate each pair of numbers. To further facilitate their thinking, the students were required to make the observation that the number of matchsticks required at any stage is actually 1 more than twice the number of triangles. So a row of values was added to the table to help the students identify the relation. So in this case, again, the number of triangles constitutes the first row of the table. But please note that an n has been introduced. The variable n denotes the number of triangles at any stage. But in the middle, a row was introduced where they just had to write twice of the number in the first row, in which case they landed up with the sequence 2, 4, 6, 8, and so on. And the actual number of matchsticks is just 1 more than these numbers. Then they were told that if n represents the number of triangles, then twice the number of triangles is 2n, and the number of matchsticks would then be 2n plus 1. So this tabular representation helped them to arrive at that general term, which is 2n plus 1. Now, most of the matchstick problems that students encountered in their middle school textbooks led to arithmetic sequences where the differences are constant. So there tends to be a feeling that most sequences that are there would always have a constant difference. That is not the case. For slightly older children, we could also bring in fractal explorations, and these can be a very interesting source of generalization tasks. For example, let us look at the Sierpinski triangle. The Sierpinski triangle is an equilateral triangle. So let us assume that there is a cardboard piece. There's a triangular cardboard piece in the shape of an equilateral triangle. And we join the midpoints of the 3 sides of the triangle so that we get 4 smaller triangles, and then we remove the middle triangle. So what we get is this. So the middle triangle has been removed. There's a hole here. So you get 3 smaller black triangles. And now, since it is a fractal, the same thing is repeated iteratively. So this process of marking the midpoints of the 3 sides, forming 4 smaller triangles and removing the center triangle is repeated on each of these 3. And then we get this. We have 9 smaller triangles here, and the same process is repeated. And now we get very small 27 smaller triangles. And a fractal pattern is actually generated like this. And let us mark these as stages 0, 1, 2, and 3. So the initial stage is always referred to as stage 0 in a fractal construction. Now the questions that can be asked is, the diagram shows here till stage 3. So how many shaded triangles, that is black triangles, will there be at the 4th and 5th stages? Can we find a rule for the number of shaded triangles at the nth stage? Or the shaded area at the nth stage if the area at stage 0 is 1 square unit? So you notice that the first question, where you ask for the number of shaded triangles at the 4th or 5th stages, is actually generalization by analogy, whereas finding a rule for the number of shaded triangles at the nth stage or the area at the nth stage is generalization by extension. And further, students can be asked to intuitively see what happens as n, the number of stages, increases indefinitely. So to proceed further, children generally enjoy fractal constructions very much, and their thinking can be scaffolded. So let us look at the 4 stages here, and let's mark the stage numbers as 0, 1, 2, 3, 4, and the nth stage will be marked as stage n. Now, the number of black triangles in stage 0 is only 1, whereas in stage 1 you have 3 black triangles, in stage 2 you have 9 black triangles, at stage 3 you have 27 black triangles, and so on. And we notice that the number of black triangles actually form powers of 3. So at stage 1, there are 3 triangles. At stage 2, it is 3 square. At stage 3, it is 3 cube, and so on. So at stage n, there would be 3 raised to the power n black triangles. But if you look at the shaded area, so if this area is 1 square unit, then the shaded area at stage 1 will be 3/4 of this. And the shaded area at stage 2 will be 3/4 of stage 1, and so on. So the shaded area forms a sequence 1, 3/4, 3/4 square, 3/4 cube, and so on till 3/4 raised to the power n. So students can explore the geometric sequences which come up in this situation, where the number of black triangles forms a geometric sequence of powers of 3, where the multiplying factor is 3. So instead of a common difference, there is now a common ratio or a multiplying factor of 3. And in the sequence of shaded areas, there's a multiplying factor of 3/4. Also, as n approaches infinity, the number of triangles increases without bound, whereas the area approaches 0. So this is a very interesting geometric exploration which children can do. They would have great fun in drawing, doing the pictorial representations and drawing the Sierpinski triangle to higher stages, and also engaging in generalization by analogy and generalization by extension. So it is important to incorporate meaningful generalization tasks in the teaching of algebra through the school years. For young children, patterning activities with concrete materials such as blocks, counters, and tiles could be very meaningful. So instead of showing them patterns and asking them to identify patterns, they could be encouraged to create their own patterns. Pictorial representations of growing patterns which bring a good context for generating number sequences also provides opportunity for generalization tasks for middle school students. And I strongly recommend fractal explorations here. Introducing numerical sequences in different forms such as arithmetic sequences, geometric sequences, and other kinds of recursive sequences such as the Fibonacci sequence will familiarize the student with different contexts for engaging in generalization by analogy and generalization by extension. So I would like to end this video session here by summarizing that we have explored the processes involved in abstracting and generalizing patterns. We've looked at generalization as the core of algebraic thinking. We discussed 2 kinds of generalization, that is generalization by analogy and generalization by extension. And we also discussed how scaffolding children's thinking towards generalization can be done using a variety of tasks. With this, I would like to share with you a few references which were used in the preparation of this video session. Thank you very much for your patient listening. I do hope you found this video session useful.